Welcome to the lecture series on GPU architectures and programming. So, if you remember, in the last lecture we have been discussing about Bitonic sort, and our discussions progressed up to the part where we are generating the Bitonic sequence. And just a small recall, so this was the CUDA code we were showing for the Bitonic sequence generation. So, each of the threads were responsible for bringing in two values into the shared memory. Then each of the threads, as we can see from the previous picture here, that each of the threads are tasked with the following operations, like if I look at the thread ID 0, then if I try to figure out that what are the values on which that thread ID is working. So, we have a nice example here on the first part here, that so thread ID 0 is bringing two values, and in the first phase of operations thread ID 0 is doing a comparison here, whereas thread ID 1 is doing a comparison here, thread ID 2 is doing the next comparison, like that. All of these are happening in this constant of in this with the variables of size equal to 2 and stride equal to 1. As you can see, the stride is 1 here for the comparisons, and the size equal to t denotes that essentially we are doing a Bitonic merge with size 2 here, right? Just between two elements here, that because that would be the first phase of the Bitonic sequence generation creation. In the second phase, again we will have size equal to 4, and we will just apply the same logic, right? But now we will try to do it with since we are doing it size equal to 4, then we will have two strides, stride equal to 2 and stride equal to 1, and in these strides thread ID 0 would be tasked with doing this this first comparison here with stride equal to 2, and then when the iteration of the inner loop goes to the next iteration, then thread ID 0 would again will be doing another comparison with a reduced stride of 1, because in the inner loop, as we have discussed earlier, the stride is decreasing by half, right? It is starting from size by 2. So, we start from stride equal to 2, and then we move to stride equal to 1. And similarly, when we started with size equal to 2, the stride was already half to 1, and there was no further progress, right? So, the outer loop is controlling the size, and the inner loop is reducing the stride starting from size by 2, and in that way I have different phases of the Bitonic sequence creation. As we have discussed that recursively, these are all basically Bitonic merge operations at different levels, right? So, just as an example, as we can see that here we have a small Bitonic sequence getting generated, 7, it increases to 8, then 11 decreases to 9, and then again this is being going to the Bitonic merge stage here in the step 2, right? So, in that way we have the above code here, which is realizing the Bitonic sequence generation part using these two cascade of loops, right? So, overall of course, the lecture slides will be with you. If you take a closer look, you will find, as we have discussed many times earlier, each thread is loading two values into the shared memory at an offset of shared size by 2. Then each thread gets into this loop cascade. Then each thread in each stage of the loops, so the outer loop is controlling the iterations over size values, inner loop is controlling the number of strides for a specific size value, and that defines for what is the per thread activity. So, for 0 ID thread, this is the activity. For the thread with ID 1, this is the activity. For thread with ID 2, we have again marked the activities. So, the 3 IDs are marked here in red, as you can see. Similarly, for thread with ID 3, these are the activities, and so on and so forth. Now, if you look into the code, we also had these variables DDD and position, which were actually trying to compute the direction of the comparison and the position at which the comparison would happen. Just to do a check that they are really doing their job, if we take an example here for this specific thread with ID 1 in the size equal to 4, size equal to 2 case, that how is this thing really happening? You can see that this is how the direction is being computed as downwards, right, using that bitwise AND operation. And similarly, you can also compute the position and position plus stride locations here. So, just have a look. This is an example we have tried to mark out for you. Now, coming to the next part of the code, assuming that we are okay with this sequence generation idea, then the other part comes in where we are just trying to do the overall merge, right. So, as we can see that the merge is the more fundamental thing, but here what we have to do is we have to do the merge over a large size Botonic sequence. So, the first thing is inside the merge phase there will be no change of direction, right, because now my goal is fixed. So, whenever I am applying smaller versions of merge recursively inside the sequence generation phase, of course, there will be a change of direction as is happening here. So, some thread as you can see 0 is always computing the comparison side indication is down. For 1 it change it's like the comparison direction changes. For 2 the direction again changes. For 3 there is no change in direction, and these are controlled by these variables. But when we come to the overall merge stage, it's a global objective, right, that you either want to do a completely ascending output or you want to compute a completely descending output, right. So, the direction is computed once and for all, and then you enter into the loop cascade for doing the different merge operation, for doing the different sequence of comparison operations. Now, if we just go back to our original picture here, so this is my merge stage, right. So, in this merge stage, as you can see that we have a validation that directions are all same. We are trying to do an ascending output. Basically, so all the arrows are downward. We want the max values to all flow down. Now, what's happening is we have to identify what is the per thread activity. So, for each thread there will be a downward comparison happening at different stride values and at different data points. So, one thing is common, the stride value will increase by 2, right, as you can see a stride 4 comparison, stride 2 comparison, stride 1 comparison. Similarly, for each thread, right, stride 4, stride 2 and stride 1 comparison. The issue is how do we distribute the different comparisons to be done as a per thread activity. So, again that is being so this is the loop which is controlling this sequence of stride values for each thread, right. So, the loop iterations for the threads are spread over the x axis in that picture, and here for each thread you are figuring out what is the position. Once you figure that okay, I will do a comparison at this stride value for the thread, the next thing you do is you figure out what is the position of the comparison, right. Once you figure out the position of the comparison by this computation, the next thing is you just apply the comparator at that position with that stride and the direction that has been already pre-decided, right. So, with this loop the output will be ready in the shared memory. Then what you have to do is, since each thread has been tasked with loading 2 values, now the threads will also write back 2 values to the global memory, both the keys and the values, right. So, essentially this the position index computes the location for which the threads will be doing the comparisons. Like for thread 2 the locations would be here, this and this, like that, right. In that way for each of the threads the positions would be computed, with different strides the comparisons would happen. So, thread 1 would have these 3 operations, similarly 3 comparisons for each of the threads, and finally when the loop iteration ends for all the threads, I would have this value in the shared memory, which now will be written back 2 values per thread in the global memory. So, we have the example here, like so if you look at here, this is the Botonic sequence creation, right. So, this is the sequence 7, 8, 9, 11 and then 12, 4, 3, 2 ascending and then descending, right. Now, let us look at the merge operations here. So, you have this that earlier output as the input, and then we are showing that first for block 0 the direction has been decided as 1. So, everything downwards, and then for different stride values we are just trying to show here as using the example how the values change. So, for thread 0 when this activity is done 7 and 12 nothing will change, then it is looking here at 7 and 3. So, 7 will come down, and then again it is looking here and it will make 3 come down here and 2 go up. In that way, with all the other values also getting swapped through the comparators, you have the final output at here as the output of the sorting network. So, that would be our overall discussion on Bitonic sort implemented as a CUDA program. So this actually gives you a nice overview how to use a sorting network and try to create a parallel implementation of that, and that will be useful for you to do some and you can try with some large sized arrays how to make these implementations, and you can study things like how shared memory and other issues can be affecting the computation. I mean, there are many interesting issues here, like for example, how do I really configure the shared memory? Is it really affecting the computation speed? Should I compare the shared memory as a larger shared memory with a smaller L1 cache, or a smaller shared memory and larger L1 cache? What is really going to help me in this case? So these are important questions you may ask yourself. You can try in a CUDA based system for your purpose. Now we'll come to the other example that we have now, which is on prefix sum. So to understand what is a prefix sum operation, so essentially is the difference between reduction, I mean parallel reduction that we did earlier, and prefix sum is that earlier when we were doing parallel reduction, you are given this sequence of values, and all you are doing is you are only interested in this value, right? So given the operator, you are interested, assuming that it's a simple addition, it can be any other associative operator, you are interested only in this expression, right? But now we are saying that, okay, no, I also want the other prefixes being operated like this. So essentially I am looking at an output which is A0 followed by A0, then assuming this is addition, I am saying it can be any associative operation, A0 add A1, and at the last it can be A0 plus A1 plus A2, like that, and finally the addition of all the numbers, right? Let's assume that this is what I want, instead of only computing the total sum, right? So in that way, if this is the input, then a prefix sum operation should return me this entire sequence, right? Earlier when we are doing a parallel reduction, assuming it's a simple addition operation, I was only interested in this 25 value, but now I am saying that no, I want an output array which is containing the sum of all the prefixes. So in the ith location, I have the sum of values from A0 plus A1 plus A2 up to plus AI, right? Now the issue is, how can this be accelerated? Can the usual technique that we applied for computing the normal parallel reduction, is it directly applicable here? What are the ways to accelerate it and all that? Now one obvious question is here that we can have two possibilities. One is inclusive scan and exclusive scan. So inclusive scan would mean that when you are producing the output array, then at any point in any jth location in the output array, you are interested in the sum from A0 up to Aj, whereas if I say it's an exclusive scan, you are saying that, okay, you are interested in A0 plus A1 like that up to Aj minus 1. So essentially you are saying that, okay, whether I will include the element in that location in the sum, or whether I should exclude it, and I will just put there the value which is for the location up to the previous one. So if I am doing an exclusive scan, then considering this A0 up to An minus 1 as my input, the output that I am looking at is, and at the initial position I am not having A0. What I am having is I, which is the identity of the operation that is being given here. Considering that the operation is addition, the identity would be a 0, so I would write a 0 here. In general, I am just writing the identity as the operator, the identity of the operator under question. So here, considering addition, I will have 0. Then the next location, that is the 1th location, I am just having A0. In the second location, I am having A0 plus A1. So in the second location, I am having the sum of the first two elements. In the third location, I am going to have the sum of the first three elements, and so on and so forth, right? Whereas if I have done an inclusive scan, in the second location I would have put A0 plus A1 plus A2 like that. So this is a example by figure that if I am doing inclusive scan. So, this is the situation for an exclusive scan, right. Now, what would be the situation for an inclusive scan? By the way, I mean you may be wondering why we are suddenly using this word scan here, because in general this operation is popularly known as a scan of the data under question, right, a scan of an array. So, when I say it's an inclusive scan, the picture would ideally be looking like this, that suppose this is your input array and your output array is being computed through the stages like this, that 3 plus 1 is 4, 4 plus 7 is 11, like that. So, if we just take an example of the code for inclusive scan, it's going, I mean this is a normal sequential code, of course it's just a simple for loop, right. Please take a second and have a look. All you are doing is you are accumulating the values in the output array. So, in the jth iteration you are computing I equal output j as simply the previous iteration's output plus the current input current location j value for the input array, right, input j plus currently accumulated value in output j minus 1. This sum is naturally going to give you the output j value. So, this is nothing but the way you are sequentially iterating over. So, that is essentially that code is basically the behavior like this, that one thread of computation iterating like this and providing the output array values. I hope this correspondence is clear to you. So, in a sequential code, this is how the program flow will go. You are just accumulating the value here and you are just considering the previous accumulated value, and so that is, let us say in this iteration you are considering the previous accumulated value output array's location here. In the current location of the output array j is equal to 1. So, this is your output 0 plus input 1, right. Then output 1 plus input 2 should give you output 2, output 2 plus input 3 should give you output 3, so on and so forth. Now, of course, these are it's very easy to understand that this is a completely sequential code. So, the work complexity is pretty high for such a simple operation, and since there is lot of possibilities for parallel execution, we can just do things in a smarter way. So, consider for initial parallel implementation. So, this is Hillis or Still scan. Consider this algorithm here. So, what we write here is a parallel version of this for loop. We are trying to say which are the operations we are going to do in parallel. So, for every location k, right, we are saying that okay, there will be some parallel additions going on, and the number of stages of the parallel additions would be log n, right. So, we will be doing log n number of stages of parallel addition, and in each stage what are the parallel additions we will be doing? It would be that every kth value should be summing up its own value with x k minus 2 to the power d minus 1. So, d is the current stage value, right. As you can see, it is quite simple, it is initially d equal to 1. So, I am just saying that okay, every thread should be summing up its location's value with the previous value, that is all, right. So, if d is 1, so then x k minus 1 plus x k, right. So, this is what is going on, right. If we just look at the data flow here, so this is the initial array. For d equal to 1, what we are doing is for every thread I am just summing up its value with the previous location's value, right. So, of course, I would need half the number of threads as is the number of locations. So, this gives me the sums, right, summation. These are partial sums that I am computing. For x1 location I have the summation x0 plus x1, right. For x2 location I have the sum x1 plus x2, like that. So, I hope this is clear. For let us say for x6 I have the sum x5 plus x6 and so on and so forth. Now, as I go to d equal to 2, let us see what happens. So, now in the second stage my stride is increasing, right. For the threads I am increasing my stride. First of all, how many threads are now operating? If you see, I have started initially with a 8 sized array, and the number of threads I am operating is basically 1 less than the total number of locations, right. Since my total number of locations is 8, I am operating here with 4 threads, right. Of course, that is required because every thread is going to add its own locations value along with the previous preceding locations value. Own location means if I am assuming a access expression which is identity. So, just location x for TID, right, x as TIDth location, that is what I would say. So initially I really do not have half number of threads of the array because every thread is going to add its own location plus the previous location. So, if the total is n here, the number of threads would be n minus 1 that are active here. Now, what happens in the next iteration? As we can see with d equal to 2, so here we will get k minus 2, right. So, every location will start adding up with one hop, right, with we'll start doing a work in stride of 2, right. Now, if that start happening, how is it first of all helping me meet the objective? So, again if we just consider that what are the total number of threads that are required here. So, first of all that would be n minus 2 because I have 6 threads operating here, but the issue is why is this working fine? Let's inspect that. So, here I have the value x 0 plus x 1, right. Here I have the value x 1 plus x 2. Now, if I add this with x 0, I get x 0 plus x 1 plus x 2 here, right. If I look in here, I have x 0 plus x 1, here I have x 2 plus x 3 operating at a stride of 2. If I add, I get x 0 plus x 1 plus x 2 plus x 3. So, x 0 up to x 3, right. Similarly, if we just check x 4, x 5, x 6, x 7, add them up, so x 4 to x 7, right. Now, if we go to the next stage, which is d equal to 3, and that should be the last stage here because your n is 8 and log n base 2 would give you d equal to 3. And now you say that okay, now what is my stride value? So, since d is 3, so to the power 2, so that means now the threads would operate at a stride of size 4. So, you start with a stride of 1 and you are just multiplying your strides, right, by 2. And of course, this should now work. Why? Because first of all, let us again write the number of threads you have active. So, here you are working with n minus 4 threads is just you are just subtracting the number of threads that are you are basically subtracting the stride value from n because every thread is operating with that stride value. So, you can surely have that many threads less, as simple as that. So, now if you look at the correctness of the algorithm is very easy to figure out because here I have essentially computed the sum up to x 0 to x 2, right. Now, if we look at a hop like this, so where do I have the sum from x 3 up to the next 4 values x 3, x 4, x 5, x 6 which is sitting here, right. What is their distance? They are sitting at a hop of 4, right. So, if I consider these two, I get x 0 to x 6, right. So, that is the inclusive prefix sum up to this point. If I consider this point and this point, what do I really have here? I am having x 1 to x 4. I have here just the x 0. So, I will just add them up and I would get x 0 to x 4. Right. So, I would get an x 0 to x 4 here. just take another example and another location. So, as we can see that here I have x0 to x1 and look at a hop of 4 from here. So, from here you have x2 to x6. So, if you just add them up, you have x0 to x2 to x5, and so you will add up and get x0 to x5. You can easily write a formal proof of this, it's quite easy to figure out. So, essentially we can understand that this algorithm is working, right. We are not going into the formal proof because that would more be a part of our algorithm course here, but all we are trying to introduce here is how the algorithm works. It's easy to figure out. Every thread adds its neighborhood values at the shortest distance, and then in the next iteration it goes to add the values from already accumulated in the neighborhood, and next it goes on increasing its horizon, and finally every thread will end up, the way the accesses are designed, every thread will end up computing values from the initial up to its location, right. So, with that maybe we will end this lecture, and in the next lecture we will try to figure out the more refined versions of this algorithm and how this can be implemented and what are the technical issues with this. Thank you.